Okay, so I welcome you in the lecture 3 of radiation heat transfer. So today we will continue with the surface properties of radiation that we have started in the previous lecture already. That is the absorptivity, transmissivity and reflectivity. We will go through them deeply in this lecture. Now before that, let me ask you a question, that why do we uh, talk about the assumptions like gray body or diffuse surface, diffuse properties and all? Why do we do that? Okay, so the answer is very simple and it is of one line, that is to make our life simple. Okay, to show that, if I draw a graph of the, okay, I lambda, okay, I, that is a function of lambda, theta, psi, everything, that is the radiation intensity versus lambda. Okay, then this graph is I am drawing for a black body, clear? Okay, and now if I look about the distribution of a real surface, that will be something like this, a very ugly distribution. Okay, so this is a real surface. Okay, in between there is another distribution like this. Okay, and this red distribution is of a gray surface. Now some of you will directly jump out of your seat and you will argue with me that what the hell, you told that things will not vary with respect to lambda. Now this is our problem, that we take the things very lightly and we think that things are not things are not varying with lambda. No, there is no things, you have to be very specific that which is not varying with lambda. Surface properties are not varying with lambda. Only if I tell you that the radiation intensity for this particular source is of gray nature or is of diffuse nature, then only this I becomes, then only this I becomes I, that is a not a function of lambda or not a function of theta or psi, but only if I do specify that that is my incoming or outgoing radiation from this source or from that source, if that is of gray nature, or if that is of diffuse nature. Diffuse or gray, now if I say that it is a diffuse surface or gray surface, or it is a diffuse body or a gray body, that does not mean that the incoming or outgoing radiations uh, are invariant with respect to lambda and theta and psi. Okay, only the surface properties are independent of those. Okay, so here it is a gray surface, that means the the properties like epsilon, alpha, then gamma, then tau, these are not a function of lambda. Okay, and in other words, I have already defined epsilon like what you are emitting, that is, if it is I mean the radiation intensity, uh, radiation, I mean the emitted radiation intensity. Okay, so I will keep a superscript E here, that is emitted radiation intensity, intensity of the radiation that is emitted by a body. So if it is a real surface, then it will be a function of this thing, also a function of T, and if it is a black body, then it will be IEB lambda. It is not a function of theta and psi, because black body is by definition a diffuse emitter. Okay, so this is not a function of lambda. Okay, so the if I draw a straight line like this, a straight line like this, then at any lambda, maybe this is some lambda 1, okay, at any lambda we will be having these two i's, now this I and this I. So this I will be what? I of I emission of real surface, okay, or I should say a gray surface, okay, and this is the I emission of a black body. So the so they will hold this property, that this will not be a function of lambda, okay. So they will hold that I gray emissive by I B emissive is not a function of lambda. This is what is a gray body, that is the surface surface properties or the body properties like transmissivity, absorptivity, those things are not a function of lambda. If I say diffuse body, then they will not be the function of direction, that is theta and psi. Clear? Okay. So now let me go into deep analysis of the surface properties. I mean, don't be afraid. Deep analysis means these are very obvious things. Okay. So we have already studied what is called emissivity. So let me just go back that what we have studied. Okay. We have studied the basic definition. Okay. Now we will study something like spectral. Uh, can you just wait? My mother is calling. Sorry for the interruption. My mother was calling for some urgent issue. I had to take the call. Okay. So let me continue. So spectral directional spectral directional emissivity. Okay. The moment I say spectral, you should identify that that means my emissivity is a function of lambda. The moment I say directional, instantly you should identify that my emissivity is a function of theta and psi, and it is also a function of temperature. Okay. So we define this spectral directional emissivity by the sign subscript lambda and superscript dash, and it is a function of lambda, theta, psi, comma t. Okay, and it is defined as my I of a real surface, and which is dependent on again all these things lambda, theta, psi and t, and by my I black body I b lambda. Now I can put a dash here, but I know that my lambda is not a I b lambda is not a function of theta and psi. So essentially this is, you can think that if at a particular temperature, at a particular direction, so if I consider a surface and I know that at this direction, okay, this is the direction at which, or I should draw a straight line because I am calling it a radiation ray. Okay, so at this particular direction, so this direction is maybe S cap, a particular radiation ray is going, and that is having an intensity of I lambda dash. Okay, now at this direction itself, this black body will also have a, radiation ray going out, that I can show like this. Okay, I mean ideally I should show it with a bigger arrow. Okay, so array yaar. Okay, so it is like this. Okay, so this is I b lambda. Okay, so now if I change the direction, then this I b lambda will be same, but this will change. Okay, if I change the lambda, then this will also change and this will also change. If I change the temperature, this will also change and this will also change. So this is the concept of spectral directional emissivity. Emissivity means energy emitted by a real surface compared to energy emitted by a black body at that temperature. Clear? Now we will learn something called directional directional total emissivity. Emissivity. The moment you are seeing directional, then you know that emissivity is a function of theta comma psi. The moment you say total, then you know that I am talking about emissivity which is being integrated with respect to lambda. Clear? So that means I have to calculate that how much energy is being emitted by a real surface, okay, throughout the wavelength range. Throughout the wavelength range. What does that mean? That is, let me write it, energy emitted by a real surface, okay, from 0 to lambda wavelength range is equal to what? I dash lambda, which is a function of theta psi lambda t d lambda. I have to integrate from 0 to infinity. Now the same thing, that is energy emitted by a real surface. Now the same thing, blah blah blah, by a black surface. Okay, black surface. Okay, now I can pose you a very interesting question. I will not give the answer of this question. That is it, is it necessary that all the surface that appear black to us, all the surfaces that appear black to our eyes, is it necessary that those are black body? And is the converse is true, that is all the black bodies, so if you are saying that it is a black body, then is it compulsory that it will appear black to us? And is the vice versa also true? So it is a very interesting question. I will not give the answer of this question. You have to think. You have to think, and for this I will give a hint that how can we see the colors of the things? I mean, why you are seeing this red apple as red? Why you are seeing this green leaf as green? First think about that and then think about the question that I have asked and put that in the comment box, the answer. Okay. Now what I was telling is that the energy emitted by a black surface from 0 to lambda wavelength range, okay, wavelength range, that will be equal to 0 to infinity IB lambda theta psi lambda t d lambda. But again I have done the mistake, that is it is not a function of theta and psi lambda t d lambda. Okay, so this is the thing. Clear? Okay, so my directional total emissivity is defined as, now eta directional, that means I will have a dash here, but now I have integrated over d lambda and I have put the limits from 0 to infinity. That means it is now is not a function of lambda anymore. So this lambda subscript will not be there, clear, and this will be equal to 0 to lambda I dash lambda theta psi lambda t d lambda 0 to lambda I v lambda, okay, this thing. So this is called directional total emissivity, clear. So this is how you should think about the radiation things, and obviously this is also a function of temperature, okay, this is also a function of temperature, okay. So and also this you can think of this, okay, no, this is correct, this is okay, fine. But you also know that this is, I mean, this is just another, I mean, representation, that this thing is nothing but your ev lambda lambda t by pi, okay, or okay, and if you put this thing, then this actually comes, okay. Now you see, this is just a different representation. Now that means this denominator part, this part, okay, this part actually becomes 0 to lambda ev lambda lambda t by pi d lambda, right? You can take this pi outside, and what is remaining is this thing, right? And if I use the Planck's distribution, then I have already shown you that this part is nothing but sigma t to the power 4. That means this is sigma t to the power 4 by pi, okay. So you can say that this total part in the denominator is sigma t to the power 4 by pi, okay. So I think it is clear. So we have done directional total emissivity. So now the counterpart will come, and that is nothing but hemispherical spectral emissivity, okay. So the moment you see spectral, that means you know epsilon is a function of lambda, and the moment you see hemispherical, that means this will be integrated with respect to theta and psi throughout the hemisphere, okay, hemisphere. Now I have already asked you this question, that why hemisphere and not sphere. The answer is, if you think of a surface, then for this surface there is nothing in this direction, okay, if it is a solid, because for solid radiation is dominantly a surface phenomena. Then if I consider that uh, I mean my range of direction, then if I draw this, then see, my range of direction will vary from this to this, or this to this, like this, okay. It will not come like this or this or this in this plane. Like if you think that this is your theta equal to 0, this is your theta equal to 30, 90, then 270, sorry, then maybe 135, and maybe 180. But after this, at this zone there is no direction. So for a surface of a solid, my direction is defined within this hemisphere. Okay, because, and why hemisphere? Because there is other plane, I mean this is a plane and not a line, so it can be like this also in this surface. Okay, in this surface it can be like this. Okay, in this surface it can be like this. Clear? So this thing and sorry and this thing, okay, this thing and this thing will define a hemisphere. I hope that you have understood. If not, please comment that I have not understood. I will tell it again you might in my future lectures maybe. Okay, so integrated with respect to theta and psi throughout the hemisphere. That means clearly now I will write it directly. So now it is hemispherical, so I have integrated with respect to theta and psi and I have put the limit. So I will only put this lambda, but I will not put this dash here, this will not be there. So it will be a function of now what, only lambda and t. Okay, now this is defined as energy integrated. Okay, so sorry, radiation energy which has been integrated throughout the direction. Okay, so integrated over the hemisphere, we write it like this: I real surface, so theta psi lambda t, we have to integrate over the whole solid angle. Solid angle is the representative of direction. This is IB lambda. Okay, again same mistake. This is again okay. Now this is fine. Okay, and now you can put instead of this lambda sine theta d psi, then you have to put the limits of psi and theta here. Now you know the limits, that is psi is from 0 to 2 pi and theta is from 0 to pi by 2. Okay, and now if you have to complete this, okay, so in this notation I will write the theta and psi thing. Okay, so psi equal to 0 to 2 pi, theta is equal to 0 to pi by 2. This will be I lambda dash theta psi lambda t sine theta d psi. Okay, so now this thing we have already derived, that this total thing is nothing but our pi. Okay, so I am just removing these things because I have already done in the next step. So this is our spectral hemispherical emissivity. Clear? I hope it is clear. Now the final thing comes, we have integrated with respect to wavelength, we have integrated with respect to direction. Now we will integrate it with respect to both simultaneously. Okay, so it is called total spectral total hemispherical emissivity. Okay, so actually these words will define that whether you have to integrate these fellows or not, and you have to integrate with respect to what. Okay, so let me complete it fast. Now in at this time it will neither be a function of direction and neither be a function of wavelength, because it has been integrated with respect to both of them. So it will only be a function of temperature, and it will be again, now there will be three integrals with respect to theta, psi and lambda. Okay, so lambda equal to 0 to infinity, psi equal to 0 to 2 pi and theta equal to 0 to pi by 2. It will be I lambda dash theta psi lambda t sine theta d theta d psi d lambda, and by what, by again the same thing, the same integration will be above and below. Okay, now in below we will have our very generous fellow which does not give us the tension of theta and psi, that is our ib lambda, again sine theta d psi d lambda. Clear? So that will be nothing but our pi ib. Okay, and this actually we know, this is what, this whole fellow we know very well, this fellow, this is the total thing integrated. So I can write this as our what, pi I b lambda lambda t d lambda from 0 to infinity, and this is what, 0 to infinity e b lambda t e b lambda, which is a function of lambda t d lambda. If we put the Max Planck discovery, then it will become sigma t to the power 4. Then the whole denominator becomes sigma t to the power 4. Clear? Okay, so we have completed the emissivity part. Now we will start one by one. Okay, what? Spectral hemispherical absorptivity. Okay, absorptivity. Clear? So now uh, absorptivity means what? So here again I have to write, it is a function of now lambda because it is spectral. Sorry, I will have to start by not hemispherical but the most general case, that is directional, right? Now you know that I have to put the dash here also, and it is a function of all the things theta psi lambda t. Now the definition is what? Now it is not with respect to the black body, okay, but it is with respect to the I incoming. So I will give a superscript small I that will show that it is incoming radiation, and it is also a function of direction, that it will have a dash and lambda. Okay, so it will be a function of theta psi, or to be more specific I should write theta I psi I. Okay, that is the direction through which it is coming. So it is theta incoming and psi incoming. Okay, and it is I absorbed. Okay, lambda theta I psi I lambda comma t. Okay, this is the spectral directional absorptivity. Next, what will come? We know it will be total directional absorptivity. Okay, I think now you can, by analogy, you can write this thing by yourself. So I will write the things for absorptivity, but I will not write the things for transmissivity. Again, I will write the things for reflectivity because there is a different case. So this will be total, then it is not a function of lambda, and it is a function of theta, psi and t, and then we have to do what? We have to integrate with respect to lambda. So it will be I absorbed lambda, the general thing, theta I, psi I. Okay, and these will be the function of theta of psi I also. Okay, lambda comma t, it is being integrated with respect to lambda, and that this thing also. Clear? So this is how the, I mean, you should develop the concept of radiation. Okay, so This is the thing. I mean, you should be able to write this. High lambda incoming. The same thing, you have to just write the expression. Okay. So now can you write the expression for hemispherical spectral absorptivity? Can you write that? I think you should be able to write that, right? Okay. So just for the sake of completeness, spectral hemispherical absorptivity, and that will be nothing but your, so spectral is there and direction will not be there. It will be a function of only lambda comma t, and I am not writing the thing again, but it will be integrated with respect to theta and psi, 0 to pi by 2, 0 to 2 pi. The same thing with respect to sine theta d psi. Here also theta psi 0 0 pi by 2 2 pi, same thing sine theta d psi. Okay. Now the last thing I will not write. Okay. So that is total. Okay. Total hemispherical hemispherical absorptivity. I will not write this. You have to just integrate with respect to the thing, with respect to uh, direction as well as the wavelength. So this is denoted by only alpha, and it is only a function of temperature. Okay. So you have to write the expression. This is your homework. Okay. I think you can do that. So we need to repeat the same thing for transmissivity. So all the things, that is all the combination, spectral, hemispherical, hemispherical transmissivity, transmissivity. Okay, then comes spectral directional, sorry, yes, spectral directional transmissivity, then comes total directional transmissivity, then comes total hemispherical transmissivity, all the things. Okay, the same definition types. But now a very interesting property I will talk about, and that is reflectivity. So now we will write spectral bidirectional reflectivity. Now why this strange word is here, that is the bidirectional thing? So you see that for reflection, I mean for transmissivity and the absorptivity, these things are the functions of theta I and psi I only, that is only of the incoming ray. But now this incoming ray, okay, can come from this direction or from this direction, it can come from any direction throughout this hemisphere. Okay, so we take that this is the direction of the incoming ray, we denote as S subscript I. Okay, now I can have my reflected ray like this in any direction. in any direction, it can get reflected in the same direction also, in this direction also, in this direction, any direction. So I will tell this direction as IR, sorry, S cap small r. So then this S cap I will have, or will be a function of theta I comma psi I, and this will be a function of theta r comma psi r. Okay, so my reflectivity is dependent on both these directions. One is this, another is this, right? Therefore my reflectivity gamma, it is bidirectional, so I will put 2 dash here. It is spectral, so I have to put lambda here. It is a function of theta I psi I theta r psi r lambda t. Now it is defined as my I lambda dash, that is incoming, oh sorry, that is being reflected, that is which, how much fraction is reflected. Okay, now this will be a function of all the things, but my I incoming, it is only a function of this. This is also very important. Okay, now how much will be reflected, that is also dependent on what is coming, because if nothing is coming, then nothing can be nothing can get reflected, right? So how much is being reflected? Okay, how much is being reflected, that is also dependent on these directions, right? That is also dependent on these directions. Clear? So now okay, so now I hope you are clear with it, that is why this is having theta I and psi I, right? Because what will be getting reflected, that is dependent on from which direction this is coming. Okay, or in other words, you can see it like this, that is, in other words, you can see it beautifully like this, that is my I lambda r is equal to I lambda dash I, that is a function of theta I psi I lambda comma t, into my reflectivity, this thing, okay, theta I psi I theta r psi r lambda comma t. Now you see here, this is a function of theta I and psi I only, but this is a function of theta I psi I theta r psi r. So that means this is a function of theta I psi I lambda t and theta r psi r. Clear? Okay, so let me continue. Now I will define something like what, the most easy thing now, that is the total bidirectional reflectivity. Okay, if I define it, then I think you would be able to define this. This will be like this. Okay, and just I have to integrate with respect to lambda whatever is there, d lambda 0 to alpha d lambda. Clear? Okay, now if I have to define what, spectral, okay, hemispherical hemispherical directional reflectivity. So by definition, this talks about the incoming thing, this talks about the reflected thing. Okay. So that means you have to integrate with respect to, so this will be integrated with respect to the incoming directions. Incoming directions. Okay. Or theta I comma psi I. Clear? So I will just write it. It will be this. Now it is hemispherical directional, so it will have only one dash. It will be spectral, it will have lambda, and this is a function of lambda. Now it will not be a function of theta I psi I anymore. It will only be a function of theta r psi r and t, that is equal to, okay, I will write it in the next line, that is equal to integration with respect to my theta I psi I, corresponding limits will be there, 0 to pi by 2 and 0 to 2 pi. I am not writing that. So I double this thing, lambda, okay, lambda theta I psi I theta r psi r t sin theta I, okay, sin theta I d theta I d psi I, okay, and you have to integrate this thing also. I, okay, so this was the reflected, and this is only having one direction. Okay, I incoming lambda theta I psi I t d lambda. Clear? Now similarly, sorry, not d lambda, what I have written, it is actually d sigma, and d sigma is, sorry, sin theta I d theta I d psi I. Clear? Okay. Now if I write for the other thing, that is my spectral directional hemispherical reflectivity. If I write this, then what will happen? Then this will be integrated with respect to what? Theta r and psi r, right? So then just we should quickly write it. This will have one dash lambda. It will be only a function of theta I psi I lambda and t. This will be defined as our theta r psi r I lambda reflected, and that will be a function of all the things. Okay, theta r psi r and lambda comma t, but now it will be integrated with respect to sin theta r d theta r d psi r. Okay, so then it will be theta r psi r I lambda I theta I psi I lambda t comma again sin theta r d theta r d psi r. Now can you see a very interesting thing, that is, this is already not a function of theta r comma psi r. Okay, so I can take this out, and if I choose this fellow separately, okay, then I can write that I can take this fellow out, and we already know that what the remaining quantity is, right? That is what? That is uh, okay, I think I have missed a little bit thing. Okay, and that is I have missed a little thing everywhere. Okay, okay, I have done a big blunder, but that blunder can be uh, corrected with a single strike. Okay, so I have already told you that if I have to find the energy at a particular direction, okay, energy at a particular direction, then I have to multiply with the cos theta. Okay, I have to multiply with the cos theta also. And why that is so? I have missed that everywhere. For this reason, I have already shown you. I am really sorry. This is the result of not, revising the things before teaching. Okay, see this expression. Did you remember that why I have put this cos theta here? Because this thing is this I thing is I am defining, okay, this I thing I am defining by dA projected, and all the things are there, d lambda, d sigma, by but dA projected. Okay, and this dA projected is equal to dA into cos theta, dA into cos theta, and this cos theta is s dot n. This I have described, right? So whenever I am integrating the I with respect to the direction, okay, then I have to take care of this cos theta also. Why? Because it is coming on a particular area. The moment I am integrating with respect to the direction, then the integration means all the information of that direction will be lost. And if I have to take care of this fact that after the integration no information of the direction should be there, but this is here to take care of the information. Okay, so I have to take care that this s dot n should be there in everything. Okay, I really just apologize, I mean, this is a great mistake. Okay, so how could I do this? I mean, really. Okay, I have to spectral directional, that is okay. mm, Directional total, that is also okay. The blunder since started with here, so I have to multiply with a cos theta here and with a cos theta here. So similarly I have to multiply with a cos theta here also. So sin theta, cos theta, d theta, d psi. And you also see, if I don't multiply a cos theta here, then it will be what? Then it should be 2 pi, because integration of this d sigma over a hemisphere, that is solid angle subtended by an hemisphere, that is 2 pi. Only if I multiply this cos theta and then do the integration, then it will give me a pi. Okay, so I was having this thing in my subconscious mind, but consistently I failed to write this thing. So just please put this cos theta in your notes. Okay, and also make sure that you have understood this thing. Okay, I have already described it, but still. And here also a cos theta will be there, here also a cos theta will be there. Okay, clear. So again total hemispherical, so here also a cos theta should be there, and here also a cos theta should be there. Okay, then only it should become pi into ib lambda. Okay, otherwise not, otherwise it will become 2 pi into ib lambda. Okay, so now here again you have to multiply cos theta I, okay, and cos theta I here also, okay. So here again you have to multiply a cos theta r, okay, here also a cos theta r, clear? And the moment you do that, then you can take this out and this will become your pi, okay, into pi. Now it is fine over a hemisphere. I am really sorry about that, and I hope you have understood that why we have to multiply the cos theta to take care of this fact that if I have this area here, so this is the normal n and this is the direction through which the radiation is coming, this s, but I have to take the projection here AP, because that is the definition of the radiation intensity, because it is DAP, okay. But the moment you are integrating that, then you have to uh, so there is d sigma and d lambda also, and if I write dA, then I have to write dA into cos theta, okay. So the moment you are integrating, you have to take care this cos theta and d sigma together, because you see a very simple logic, if you put this cos theta there and then integrate with respect to d theta, then cos theta is there already. So even after integrating, you can see that this is a function of theta, we can say this is clearly a function of theta, but integrating with respect to direction means there should be no theta in this side in RHS. So you have to take this cos theta here also. So there is both the intuitive logic and the scientific logic, okay. Okay, so this was what spectral directional hemispherical reflectivity, clear? Okay, so the denominator would be I lambda dash I, that is a function of theta I psi I lambda t into pi, clear? Okay, now finally we say that we have to calculate total bidirectional, sorry, hemispherical reflectivity, total bihemispherical reflectivity. Okay, so that means this will be I mean dependent as, okay. And some in some books we write it like this, that is this will take care of the word directional, after that we will have a hemispherical, and here then we will have first hemisphere then directional, okay. So that means you can write, you can draw here two hemisphere and one lambda, oh sorry, no lambda, okay. Then you can write this as, you have to integrate, there will be four integrals, theta I psi I theta r psi r, and this total thing with respect to d omega r or sin theta r d psi into cos theta r, okay, and d omega I into cos theta I. The similar four integrals, theta I psi I theta r psi r, then it will be d omega r cos theta r d omega I cos theta I, clear? This was the concept. I think I have covered almost all the topic. Let me see that if any topic is left. I have a list of topics actually. From there I am counting, okay. So I think I have covered almost all the things, okay. So finally last two concepts are remaining. I will take just 10 minutes more. So say that you are given, say that you are given, so let us try a sample question. You are given some distribution of this thing. This is a function of lambda, theta, psi t. These are essentially theta I, psi I. No, sorry, not I. This is emissivity. Okay. Then from this you have to find this only. Then what you will do? What you will do? So this is having a definition, that is, this is equal to your theta psi from 0 to pi by 2, from 0 to 2 pi, and then we will be having what? I, that is actual body, lambda I, okay, this thing into sin theta d psi into cos theta. So I can write sin 2 theta by 2. Cos theta I have taken there, and then I have to also integrate with respect to this thing also for the black body thing. Okay, sorry, these are not the functions of theta and psi. Again, sin 2 theta by 2 d theta d psi, and we know that this whole thing is nothing but pi. But now you can argue with me that I don't know this, then how can I find this thing? But you know this thing, this is what given, right? So now you see, what is the definition of this? Definition of this is this thing, lambda is what? I lambda dash lambda theta psi t, and IB lambda lambda sorry, here also I have written the wrong notation, so IB lambda, okay, so here lambda and t. So now you can see that uh, from this equation you can put this is equal to this into this, right? So that means we can say that this is equal to my IB, sorry, not this equal, this is equal to, okay, this is equal to your IB lambda, which is a function of lambda and t, into epsilon this and this, okay. So now you know that this is not a function of the directions. You can take this out. The moment you take this out, and you can take this out also, so they will be cancelled out. So in the denominator there will be only pi, and in the numerator you will be having this into sin 2 theta by 2 d theta d psi integrated over the directions. Clear? Okay, I will solve separately some problems, but I hope this thing is clear to you. Okay, so I mean, now having the similar concepts, can you find, if this is given, can you find alpha? If this is given, can you find alpha? That is, this is what? Spectral directional absorptivity, and this is total absorptivity, total hemispherical absorptivity. I will solve this problems separately. What I am trying to say is, if you go back to the things, this is the absorptivity thing, okay. See, in this integration, this is actually can be replaced as, this thing can be replaced as alpha, this thing into I incoming theta I, okay, okay. I am just saying this, and from where I can get it, from here, I can get it from this equation. Similarly, for emissivity also I can replace this thing, okay, by Okay, I can replace this thing by IB lambda lambda T into this thing. Okay, so that I have got by the basic definition of spectral directional emissivity. I think it is also clear. And just please mind this cos theta thing, okay, because in the examinations also people do these mistakes. This cos theta thing should be there, they just integrate with respect to d sigma, the mistake which I have made. Lastly, I will end this lecture by stating the Kirchhoff's law. Okay, Kirchhoff's law of radiation. That is a very much intuitive law. Okay, so at a particular direction, so this surface or this body, a solid body, this is having a temperature T naught or T infinity. Ambient is also having a temperature T infinity. So if both the ambient and this body, if these two have to be in thermal equilibrium with each other, then at a particular direction, whatever is going in, whatever is going out, the same thing at a particular direction should be going in, okay. Only, I mean, we cannot say that if something is going out in this direction, that should be equal to this direction. I mean, if something is going out in this direction, we cannot say that should be equal to something going in any other direction. That can be or cannot be. I mean that may be true or may not be true. But for a same direction, if something is going out, the same direction in the same direction if something is going in, then they must be equal. Okay, only if this holds true, then if I integrate all over the hemisphere, then the total energy going out is equal to the total energy going in. Otherwise, if I say that okay, this is equal to this, then I don't know then which are these two directions. Okay, then I don't know that if there is any other direction. Okay, if there is any other direction in which some radiation energy is going out, then I don't know that is there any counter direction in which the same radiation energy is coming in, if these directions are arbitrary. So that is why we cannot say that these directions are arbitrary. Then we cannot confidently say that for any energy that is going out, we have a same energy that is coming in. Okay, only if this is true, that for the same direction, the energy that is going out, that is equal to the energy that is coming in that direction. If this is true, then only we can say that the body will surely be in thermal equilibrium. Okay, and this is the Kirchhoff's law, that if the surface is in thermal equilibrium with surroundings, okay, then your alpha, that is absorptivity, that will define that how much is coming in. Alpha lambda dash, that is a function of lambda T theta psi, is equal to your emissivity, this thing. Okay, now for a gray surface, okay, my lambda, this is not a function of lambda. Okay, that means my alpha lambda is as good as my alpha dash. Alpha dash lambda is as good as alpha dash. Similarly, my epsilon lambda dash is as good as epsilon dash. Okay, that means for gray surface, my alpha lambda dash is equal to alpha dash is equal to epsilon dash is equal to epsilon lambda dash. For a diffuse surface, okay, for a diffuse surface, my alpha lambda dash is not a function of theta comma psi, That means my alpha lambda dash is as good as alpha lambda. My epsilon lambda dash is as good as epsilon lambda. That means my alpha lambda dash is equal to epsilon lambda dash. This is my Kirchhoff's law. So for a diffuse surface, my alpha lambda is equal to epsilon lambda. Finally, for a gray diffuse surface, okay, my alpha lambda dash is not a function of alpha lambda dash, theta, psi and lambda. That means my alpha lambda dash is as good as alpha and my epsilon lambda dash is as good as epsilon. That means as my Kirchhoff's law says that these are equal to true, then only for a gray diffuse surface my epsilon is equal to lambda. So people tend to do a mistake that whenever they are asked that what is the Kirchhoff's law, they say that alpha is equal to epsilon. No, Kirchhoff's law is only this, that is the spectral hemispherical emissivity is equal to spectral hemispherical absorptivity. Only for a gray diffuse surface my the Kirchhoff's law is spectral directional absorptivity is equal to spectral directional emissivity. Only for a gray diffuse surface my total hemispherical emissivity is equal to total hemispherical absorptivity. Clear? I hope these things are clear. So this was very important, that for a diffuse surface my spectral hemispherical emissivity is equal to spectral hemispherical absorptivity, that is this. For a gray surface my directional total emissivity is equal to directional total absorptivity, that is this. And for a gray diffuse surface my total hemispherical emissivity is total hemispherical absorptivity. So with this I will end this lecture and we will continue with the other things in the next lecture. Until that, goodbye, take care and thank you.